Okay, so I want to create a C++ process object or a process class that follows the RAII idiom. That's the resource acquisition is initialization idiom. And I want to do that because when I create a process, a process is a system resource, and I may also open up other resources such as file descriptors or file streams. And I want to create an object that manages all those resources for me so that when I use it in my program, I don't need to worry about cleaning up those resources afterwards. And so let's take a look at the header file that I supplied. And so there's a constructor. I modified this a little bit from the one that I originally posted. I just simplified it and made a single constructor definition and gave the verbose flag just a default option. So you could either call the constructor with only the vector of char pointers, which will contain the program and the options which you want to start as a new process, or you can give it an optional verbose flag as well, just to turn on some extra debugging. The copy constructors we are going to leave unimplemented for now, and potentially in the future, because we don't want to allow copying of this object because we haven't really thought about what it means to copy a process yet. And for now, I'm also going to leave the move constructors empty. We'll define those later. Move constructors are the move semantics are something new in the C++ 11 standard. And so when you compile this, open my makefile, when you compile this, you're going to want to use, make sure that you're using the C++ 11 standard. So you can just put the -std equals C++ 11 in with your C++ flags. And so just make sure that you're using those flags, otherwise you'll get an error about those move semantics. That's the double ampersand. And then, so right now we want to implement the constructor and deconstructor. So in RAII, when I create an object, I want the resource to be acquired and initialized. And so in this case, the resource is the process that we want to create. And so in the constructor, I'm going to call the fork system call. And so I'm going to combine it with this if statement here. And so say if my PID is fork, and so fork returns a PID, and if that is less than 0, then an error occurred during the fork. And so I'm going to just call p_error process fork, and that will just print out the error preceded by this string here. And I'm going to throw an exception. I'm just going to throw a string object rather than write an exception class right now. And okay, so that's just in the event that the fork fails. And it's always a good idea to if you have a system call that does return a status that could be an error, check for that error and then do something with it. In the worst case, just print an error to the screen and you want to abort your program. Remember, one of the design philosophies is that when you do fail, you want to fail loudly so that the user notices right away and a potential error doesn't get hidden in layers of detail. So if PID that I get back from the fork is equal to 0, so if PID equals 0, then else if, then I am in the child. So child process, and the child is going to, at this point, just run a call to exec. And later when we do the reading and writing, we're going to have to play around with dupe2 to create a, well, we're going to create the pipe and then use dupe2 to redirect that. But right now, I'm just going to make a call to exec VP. And let's just go over here and look at the man page for exec. Exec, do they have sorry, let me do a man page for exec_vp because that shows me all the different ones. Okay, so exec_vp returns an integer, that's the status, and it takes as first argument a pointer to a constant char, and then as the second argument an array of const chars, array of const char pointers. And so I'll go back over here, and so the first argument, I'm just going to take the first element of my args vector, and so that's a vector of char pointers. So that's the first element is going to be a char pointer, and that's what it wants. Now the second argument, we can do a little trick here and do a const cast char pointer pointer, and then give it the address of the first element of that vector. So that's a standard library vector, but now I'm doing a const cast to use it as an array of char pointers. Okay, so if this exec_vp command works, we'll never get to the second line because at this point the child process will be replaced by whatever command is in the argument, the first element of the args vector here. But if this doesn't work, if there's some kind of error, we will get here, and we want to make sure that we know about it. So again, I'm just going to put a message there, and we'll also throw this process. Okay, and we can throw in some debugging or messages, so we can say not there, actually sorry, let's do, and then else. So the final case would be, we've already covered if mpid is less than 0, equals 0. If it's not equal to 0 but it's not less than 0, then we're in the parent process, and mpid contains the PID of the process that the parent just forked. And so right now, since we're not redirecting any file descriptors, there's nothing going on in the parent process, but we can just print a message if the verbose flag is set. So I'm just going to say process, and then I'm going to use the name variable, and so you see up here I just set the name, I initialize the name string to be the first element of that character vector, or vector of char pointers. And so I'm going to kind of say forked PID mpid indel. Okay. And so that's all the parent is doing at this point. Okay. So at this point, once you create the object, fork is called, the child is spawned, exec is called to replace the child image with the program that's contained in the args vector. And so that's running. So now when this process is destroyed, we want to make sure, or sorry, when this object is destroyed, we want to make sure that the child process that it started is destroyed as well. So simplest way to do that right now is just send that PID, the sigterm signal. And this might not always be guaranteed to kill the process, but we're going to assume right now it is, just to keep things simple. And then we're going to want to wait for that process to terminate before the deconstructor leaves. So I'm going to use wait PID, which is similar to wait, except wait PID, you can give it a PID to wait for, and then like the wait call, it takes a pointer to an integer that is a return status, and it also takes some options, which we can just set to 0 because that's going to be sufficient for us, and then it returns PID. So first I'm going to create my status variable, and then I'm going to say PID equals wait PID, and then the PID of the process, the child process, status, and then give option 0. So if PID returned by wait PID is less than 0, then an error occurred. So we'll say process name wait PID error. Or we'll just wait PID. Oh, sorry, wait, I can't do that here. I'll just say process wait PID. And but if no error occurred, and so if an error occurred, that's not going to happen now, but we probably want to do something about that, because this means that for whatever reason the wait PID could not get a status on the child process. But this should be good for now, and so we should be able to compile this now. Compile. And so I compiled my the process there, and then also the process test. Let's just take a look at process test. You already saw this, but so we're going to create a process object. Arguments are going to be created by the command line arguments to the process test program, and so that's what we're passing to the process object. And then we're going to sleep for 5 seconds. At this point, the process object goes out of scope, and so its deconstructor should be called. And so we're going to watch to see that the child process is destroyed at this point. And then it sleeps for 5 more seconds just to give you time to confirm that the child process is destroyed by the deconstructor of the process object, as opposed to just getting cleaned up by the system when process test finishes. So let's go back to the terminal here. And I'm going to split this screen, and down here I'm going to run watch to monitor the process list. Yes, W. And so watch just refreshes this every half second, and it runs the PSW command so we can look at the list of processes that I'm running. So I should have a child and a process test program. I'll just run child first. Child just prints incremented numbers to the screen every second, and it will do this forever until it gets some kind of signal to stop. So I just hit Control-C to stop it there. I'm going to run process test and then child. And then watch down here in the process list, you're going to see a process for this command itself, process test with an argument child, and then you should also see the child spawned as a separate process. So there it is, there's the process test child and then child, and you can see that child is running. After 5 seconds, the process object goes out of scope, and let's just run that again so we can watch that. So after 5 seconds, the object goes out of scope, and we'll expect this child process to disappear, which it does because it gets cleaned up by the deconstructor, and then 5 seconds later, the process test finishes. And so that does everything that we needed to do. So next time, we will add the reading and writing functionality to our process object. If you run the process test with some other arguments, say try, like for instance, a process that will finish before the 5 second wait is up, you can notice that down here you get this zombie process. So the process finished before the process object cleaned it up. And we can also solve that, not that it's a big problem, it gets cleaned up after 5 seconds, but you can actually use signals to signal the parent process when the child process is finished, and then just so the parent is aware of that and can clean up any resources too. But for now, this is all we need.